Okay, so this video will serve as a review for test 1. So test 1 will cover pretty much everything in chapters 11 and 12. Although there's really not a lot of questions I would ask, at least not directly, in section 11.6. Remember, 11.6 were the quadric surfaces and cylinders. Obviously, you should know what these surfaces are, but I'm not going to ask, what's this the equation of? Is it a cylinder? Is it a hyperbolic paraboloid? Is it an ellipsoid? So you don't have to memorize all those equations because those will be given. It's what you can do with those equations, and maybe convert them to cylindrical coordinates or spherical coordinates. That's in 11.7. Okay, so nothing directly from 11.6, but again, you should be at least aware of what those surfaces are and some of their properties, for example. But yeah, so everything else I think is fine. Okay, so mostly what I plan to do is just go over some of the problems on the practice test. Again, the practice test is available in Blackboard. You can download it, print it out, and just think of that as practice for the test. Right? It's a lot of problems, and if you were going to do all of them, I think there's 32 of them. That could take you 5-6 hours. Take you even longer than that if you really want to make sure you do all of them correctly. Again, if you have the time, I would suggest doing as many of them as you can. And you can check in the back. The answers are back there. But in most cases, with very little explanation, it's just the answer. So you can check to see if you're right. And be aware that there are still some typos in the answer key. So if you get something wrong and you're convinced that you're correct and the answer key is wrong, just send me an email or just ask me. And it is possible that some of them are wrong, but most of them are correct. I'd say 99% of them are correct in the answers. Okay, so for the first 7 problems here, these are mostly computational. Right, so these are sort of the basic of the basics. These should be very simple. Right, so I'm not going to do a lot of these, but I'll do a few just to make sure that you really do have the basics down. Right. So for example, so we have the 3 vectors u, v, and w are given in their component form. Right. So for number 1a, just add u plus v. I think you can handle that. So I'll do b, 3v minus 4w. Okay, so the way you would calculate this is do 3 times the vector v, 2, 1, negative 5, minus 4 times the vector w, which is negative 1, 6, negative 3. So 3 times v is just 6, 3, negative 15, and negative 4 times v, yeah, I'll write it as a plus. So yeah, negative 4 times negative 1 is positive 4, and then negative 4 times 6 is negative 24, and then positive 12. So now you're just adding these 2 vectors, so you get 10, negative 21, and negative 3. And that should be the answer. So, yep, you should be able to do that, right? How about the dot product of u and v? So that's part C. U dot v. Oh, I need u and v here. Yeah. So sorry about that. So right. So on the right here, I wrote u, v, and w, so I can refer to those. So the dot product, right? 4 times 2 plus negative 3 times 1. Plus 1 times negative 5. So that's 8 minus 3 minus 5, which is 0. Right? And that tells us that u and v are orthogonal. For part D, I guess we want the cross product of the same 2 vectors, u and v. So Again, you don't have to do it this way, but I prefer to write it as a determinant. So just copy down the columns here, or the rows rather. These are row vectors. Right. So for the I component, you're going to get 15 minus 1. I can do that in my head, right? 15 minus 1 is 14, so 14 times I. And then 2 plus 20, so that's 22j. And then 4 minus negative 6, so 4 plus 6 is 10, so 10 times k. And I know I'm not being consistent here. I probably should write it as the row vector 14, 22, 10. But as I said many times, I am not picky about that. You can write them either way you want, any way you want. All right, so, and again, I think you can handle part E. It's just taking the cross product of V and W, so you got to do that first, and then take the dot product with V. Yeah, right. So so one thing I should mention about part E is that this looks ambiguous, right? It looks like, well, what do you want us to do? Do you want us to take the dot product, U and V first, or then the cross product of V and W first? Well, one way makes sense, one way doesn't, right? If you take the dot product of U and V first, you get a scalar cross product with a vector, which makes no sense. So no, you have to, you have to do it this way. You have to take, in parentheses, you do V cross W first, and then take the dot product with U. So which one should we do here? How about 2C? Right, so 2C is just take the magnitude of W. So the magnitude of any vector, we've done this many times, is the square root of the sum of the squares of the components. Okay. So square root of 1 plus 36 plus 9. So I guess it's the square root of 46. Right, which is 2 times 23, so I don't think we can simplify that. We'll leave it as square root of 46. Right. Oh, for you engineers out there, you want to approximate that. It's approximately 6.7823. But I'm looking for the exact answer, square root of 46. Right, so how about the angle between U and W? So that's number 3, at least part A. Yep, so the angle between U and W. Right. So you noticed I didn't ask for the angle between U and V because that should be automatic. Look at 1C, right? They're orthogonal, so the angle is 90 degrees. Okay, so U and W. Right, so here's U and W. So, of course, we're just using this formula, which is on your formula sheet, right? Cosine of theta is U dot W divided by the magnitude of U over the times the magnitude of W in the denominator, right? So U dot W, we never did that, but that's going to be, let's see, negative 4 minus 18 minus 3. And the magnitude of U, we didn't do that either. I think it's the square root of 26. 16 plus 9, 25 plus 1, yeah. And we did the magnitude of W just now, so that's the square root of 46. Right? So what do we get? We get, I think, negative 25 over the square root of, well, yeah, 26 times 46. 26 times 46 is 1196. Sorry about that. So I'll just write it as one big square root. 1196. So that's not the answer, of course. That's the cosine of the angle. So to get the angle, we just take the inverse cosine of negative 25 over the square root of 1196. And you can just plug that in your calculator. So 136.29 degrees. Decimal point, right. So again, right, you have the exact angle and then the approximate angle. So yeah, so not hard, right? And of course we know it's bigger than 90 degrees because the cosine is negative, so that makes sense. Projection of u onto w, sure, we can do that one also. So 3b, projection of u onto w. Let me make sure I got that right. Yep. So formula for the projection, it's going to be u dot w divided by the magnitude of w squared times the vector w, right? So u dot w, we didn't do that. Oh, we did, yeah, we did that here, right, in part A. So that's just negative 25. And then the magnitude of w was the square root of 46. So when you square it, you just get 46 times w, right? So it's just this multiple of w. So I guess what is that as a vector? So w was negative 1, so you're going to get negative, so positive 25 over 46 for the first component. The second component is going to be, 6 times that, which is 75 over 23. Is it negative? Yep, it's negative 75 over 23. And then the last component is negative 3, so negative 3 times negative 25, so that's 75 over 46. All right, so I hope I did that right. That's the projection of u onto w. Okay, so what's next? Number 4, find t such that the vector t minus 1, 8 is orthogonal to w. Okay. Oops, sorry. Yeah, so find t so that the vector, I can't use u, so I'm running out of letters here. Let's just call it r. So the vector r is t minus 1, 8. So that's just a straight line, of course. So we want this to be orthogonal to w. And as a reminder, w is just negative 1, 6, negative 3. So it's really just testing you. Do you know what orthogonal means? Right? Orthogonal, two vectors are orthogonal if their dot product is 0. So take the dot product. What's r dot w? It's going to be negative t, right, plus 6 times t minus 1. Plus 8 times negative 3 is negative 24. So what are we going to get? 6t minus t is 5t, minus 6 minus 24 is negative 30. So when does that equal 0? Yep, when t is 6. So that's a funny looking 6. Is that okay? So t equals 6. That's the value. That's the one value of t where these two vectors will be orthogonal. Number 5. Here we want to find three numbers, a, b, and c, such that a times the vector u plus b times the vector v plus c times the vector w happens to equal the vector 5 with components 5, 15, and 4. Okay. Yeah, this essentially is a linear algebra problem. And if you don't recognize it as such, that's okay. But let's just see, right, so remember what u was. U was the vector with components 4, negative 3, 1, right, plus b times the vector v, 2, 1, negative 5, plus c times the vector w, once again, negative 1, 6, negative 3, and that has to equal the vector 5, 15, 4. And these are just scalar multiples, right? So what you end up with is if you combine all this into a single vector, the first component will be 4a plus 2b minus c. The second component will be negative 3a plus 1 times b plus 6 times c. And the third component will be 1 times a minus 5 times b plus 3 times c. So when are two vectors equal? When their components are equal, right? So you end up with essentially three equations. I got to write them down correctly. 4a plus 2b minus c has to equal 5. Negative 3a plus b plus 6 times c is equal to 15. And a minus 5b plus 3c is equal to 4. So this is a system of three equations in three variables. And even if you have not had linear algebra, you should have done this a long time ago in your college algebra pre-calculus days. So I think you can take it from here, right? You can solve for a, b, and c. So that's not a hard problem at this point. Right. In fact, if you want to just use your calculator and set up the matrix, right? You can just reduce that to echelon form. Again, that's be more familiar if you have had linear algebra, right? And when you do that, this is equivalent to, let me see here, 4, 0, 0. Oh, I'm sorry, 1, 0, right? The identity matrix. 1, 0, 0, 4, 0, 1, 0, negative 3, and 0, 0, 1, 5. Right. So this is the row-reduced echelon form. Right? And it's in your calculator. You can just, if you want to just use your calculator, fine. It wouldn't be that terrible to work it out by hand, but it is tedious, right? So A is 4, B is negative 3, and C is 5. And that answers the question, right? Okay, I'm going to skip number 6 because I think you can handle that one. It's just finding the parametric equations of a line, right? Parallel to a vector and passing through a point. So it's just the definition of the equations of a line. All right, so number 7, right? We want to find the equation of a plane. So here's a plane, and it contains a point, right? So the point here is given by, right, 2, 3, negative 1. And it contains two vectors. Let's say vector u and a vector v. So how do we find the equation of that plane? Well, we need a point, right? So the equation of a plane, I think it's on your formula sheet. If it's not, well, then you probably should know it. Right? So we did this way back in section 11.5, I believe. Right? So, of course, your x0, y0, z0 is given. What you need to find is the a, b, and c. Right? And the a, b, and c are going to be the components of a normal vector. Any vector that's perpendicular to the plane or normal to the plane. Right? Now that's not given, but if it's right, if the vectors u and v are in the plane, then a vector that's orthogonal to both vectors is just u cross v. Okay? So you have to find u cross v, which was probably one of the questions that we did, right? We did u cross v, didn't we? Yeah, part D here, 14, 22, 10. So the components are 14, 22, and 10. Right, so those are my right? That's just A, B, and C at this point. So yeah, so to get the equation, we're going to get 14 times x minus x0, x0 is 2, plus 22 times y minus y0, y0 is 3, and then plus 10 times z minus z0. Oh, z0 is negative 1, right? So z plus 1 equals 0. And what I probably should have done is divided by 2 here. So maybe it's not too late. We can do that now. Right? And you don't have to, but it does simplify things considerably. Right? And now just multiply it out. Right? I think I have just enough room to do that. So 7x plus 11y plus 5z. And then what do we have? We have negative 14 minus 33 plus 5 equals 0. So negative 47 plus 5 is negative 42, I hope. So that should be the answer. Yeah, in the answer key, I bring the 42 to the other side. Yeah, don't make that an issue. It's the same equation, right? Either way is fine. Just be aware that if you want, say, the distance to this plane, then your d is negative 42, not positive 42. But, of course, for the equation of the plane, either is fine. Okay, so that should do it for the basic calculation problems here. Okay, number 8. Right, so this is our first sort of application type problem. 3 planar forces act on an object. The magnitudes and angles with the positive x-axis are 100 newtons, that's the unit of force, and 25 degrees, 70 newtons, 305 degrees, 120 newtons, and 200 degrees. Find the force necessary to keep this object in equilibrium. That is, we want to find another force, the fourth one, so that the net force on the object is 0. Find its magnitude and its angle with the positive x-axis, and round to the nearest hundredth, so 2 decimal places. All right, so this is essentially a problem you would see in a statics course or in a physics course. So let's just draw a picture. So these 3 forces are acting in a plane. So we only need the x and y plane. We don't need the z-axis here. So we have 3 forces, right? One is 100 newtons and 25 degrees. Is that about right? So we'll just call this force A as a vector, right? And then 70 newtons and 305 degrees. So, wow, 305 is 90, 180, 270, and then 270 plus 45 degrees is 305. So that's going to be, yep, that angle there, 45 degrees. Of course, I could have just said negative 45 degrees. Wait, 45? No, that's not right. 270, 35 degrees. All right, so yeah, so it's only 35 degrees, not 45 degrees from here. So it's negative 55 degrees. All right, so that's force B. And then force C is 120 newtons and 200 degrees. So that's going to be a slightly longer one, and that's 20 degrees. Yeah, so it looks like it's like opposite of angle, sorry, not angle A, but opposite of vector A. Not quite, right? They're 5 degrees off. They're 5 degrees off. In other words, if I reverse this one here, it would just be off by 5 degrees. Very hard to tell. Okay, so what we're looking for is a fourth force, and again, we have no idea where this force would be here. Maybe something like this, so I'll call this F. So we're looking for a fourth force such that they would essentially cancel all the other forces, right? So to keep all these forces in equilibrium, when you add up the forces, the individual forces, you get, right, A plus B plus C plus F. And if it's in equilibrium, that has to be 0, right? These are all vectors, so don't forget the vectors, the arrows, right? So what is F then? The force we're looking for is just going to be negative A plus negative B plus negative C, right? So essentially just add up these 3 vectors, A, B, and C, and then just take the opposite, right? Yeah. So it's the opposite of A plus B plus C. Okay, so that's the force we're looking for. How do we get there? Well, I think the easiest way is to find their components, right? We're very accustomed to adding vectors when we're given their component forms. Unfortunately here we're not, right? We're given them as in terms of their magnitude and then their angles. So yeah, I think even though it's kind of a nuisance, I think we have to rewrite these in terms of their components, right? And it's not hard, right? A is just 100 times the cosine of 25 degrees. And then the second component is 100 times the sine of 25 degrees. And right, since we're going to round later, we might as well round right now. So 90.63, and then 42.26. Sorry, not degrees. I don't know what I'm thinking about there, right? This is a force, so these are in newtons, right? All right, so I think you can handle the rest. I'm just going to quickly write them down so we can get going here. Okay, so I worked all these out, and now we can just add a plus b plus c by just adding their corresponding components. So you take 90.63 plus 40.15 plus negative 112.76. We get about 18.02. And then for the second component, you get 42.26 minus 57.34 minus 41.04. And you get negative 56.12. Okay. I hope I did that right. Yeah. So that's a plus b plus c. So the force they're looking for is just the opposite of that, right? So it's negative 18.02 and positive 56.12. Okay. So I was wrong, by the way. It's the force should be something like this. So it was a bad guess, but okay. I guess I should have known based on B, and that A and C almost cancel out, right? So something like that, right? Oh, and they want the magnitude and angle with the positive x-axis. So that's just trigonometry again. The magnitude of this vector, so the actual length of the vector, the force, is the usual formula for the magnitude. So that'll be approximately 58.94. And that'll be in newtons, right? So these are all in newtons, typical unit of force. And then for the angle, right? So we're looking for this angle here. We'll call that theta. So that's going to be arctangent of, say, F2 over F1, right? So, yep. So the inverse tangent of, let's see, F2, 56.12 divided by negative 18.02. Put that in your calculator. And you get negative 72.198 degrees, so we'll round to 0.2 degrees, negative 72.2 degrees. Of course, just looking at the picture here, that can't be right? That looks more like the angle with B, although it's actually a little more than that, but right. So yeah, you have to go halfway around. You have to add 180 degrees to this to get into quadrant 2. So it should be 107.8 degrees. Right. So there's the magnitude and there's the direction, and there's the vector in component form. So I think that answers the question for number 8. Okay, number 9. Find parametric equations of the line in the plane 4x plus y minus z equals 8, right? Or minus 8 equals 0. Passing through a point 3, 2, 6 and perpendicular to the given line, right? Right. So this is kind of confusing, right? Let's draw it out, right? So let's suppose this is the given plane here, right? And we want to find a line that's in the plane. So let's say we want to find this yellow line here, right? That's in the plane, and we know it passes through the point. Say this point right here is 3, 2, 6, right? And it's perpendicular to a line. So yeah, so it could be this line right here. I know that doesn't look perpendicular, but let's suppose it is, right? So you have to be careful, right? Because you might think that if it's perpendicular to the line, it has to be perpendicular to the plane. And that's not necessarily the case, right? In fact, the line could also be in the plane, right? You can imagine drawing a line perpendicular that lies in the plane as well. So yes, the line has to be, right, the given line here, this purple line here, right, has to be perpendicular to the yellow line, but not necessarily perpendicular to the plane. Okay, so yeah, that's what makes this a little confusing here, right? So what do we need to find the parametric equations of a line, right? Now in this case we could write it as r, as vector r of t, right? But it's just x0 plus at, y0 plus bt, and z0 plus ct. And in fact, we're given the x0, y0, z0 because we're given a point on the line. Okay, so really all we need now is just the a, b, and c. What's y2 plus bt? And then 6 plus ct. Right? So I'm looking for a vector that points along the line. So a vector that points, say, this way here. So we'll call that v, and it has components a, b, and c. Right, so is that clear how to find that vector? Probably not at all, right? Like I said, this is kind of a tricky problem. And maybe this is not the best picture here. Maybe this purple vector really shouldn't be like that. But notice we didn't do anything with the plane yet. Notice the plane has a normal vector, n, with components 4, 1, negative 1. I hope you see where I got those, right? 4, 1, negative 1. Remember, when you have the equation of a plane, the coefficients of x, y, and z are your a, b's, and c's. That's your normal vector to the plane. So the yellow line has got to be perpendicular to that vector, right? It's orthogonal to that vector. Can I draw that, right? And it's also orthogonal to this purple line. And what can we say about the purple line? The purple line clearly has some sort of a vector in that direction, right? -2, 5, -1. So I'm running out of letters. We'll call it W, right? -2, 5, -1. So I'm looking for a red vector that's orthogonal to both n and w. So this vector v, a, b, and c, how do we find those? Take the cross product of n and w. So n is, right, you could also do w and n, right? So it doesn't matter which direction it points in. So let's keep the order here. So n is 4, 1, -1, and w is -2, 5, -1. And so we should get -1 plus 5 is 4, so 4i. 2 plus 4 is 6, so 6j. And then 20 plus 2 is, right, 22k. And in fact, we can scale this down. We can divide by 2, right? So let's say the normalized vector, oh, sorry, we don't have to normalize it. But, right, it points in the same direction as this vector here. Right. So, right, so I think that should do it, right? X is going to be 3 plus 2t. Y is going to be 2 plus 3t, and z is going to be 6 plus 11t. And again, your results may vary. You might have a different answer. As long as it's, it's the same line, then that's fine. Right, notice it says find parametric equations. It doesn't say find the parametric equations. So there are other answers here, but I think this is the one that probably makes the most sense. And I'm guessing that's probably the one in the answer key. Okay, so I'm hoping 10 and 11 are fairly reasonable. They're not too complicated. And in fact, 12 is not that bad either. It's just a formula, right? Find the distance between a point and a line. Right. The only tricky thing about this is that the line is given in symmetric form, and 2m's in symmetric, right? Symmetric form, and it really makes sense to convert this to parametric form. So when you set these equal to t, you should get x is equal to 3 plus 2t, y is equal to negative 4 plus t, and z is equal to 1 plus 3t. Okay. So, yeah, so that's, right, so those are the equations of a line. That's the given line. And now we have a point. Presumably that point is not on the line, and we want to find the distance d, right, between them. Right, so of course there's a formula. So I think, if I remember right, it's d is the magnitude of vector p to q cross v divided by the magnitude of v, where v is just the direction vector for the line, and you can get that from the coefficients of the parametric equations, right? So v is just a vector with components 2, 1, 3. And why don't we just take the magnitude right now? It's the square root of 9, 10, 14, square root of 14, right? And so what is P? P is any point on the line. So pick your favorite point, right? Suppose T is 0, then P is the point 3, negative 4, 1, right? And if you picked a different point, it doesn't matter, right? You'll get a different vector from P to Q. Oops, sorry, this should be a Q here, right? Q has coordinates 1, 0, negative 1, right? Okay, so if Q has coordinates 1, 0, negative 1, then the vector from P to Q, right, will be 1, let's see, 1 minus 3, right? So negative 2, 0 minus negative 4 is positive 4, negative 1 minus 1 is negative 2. Right? Now you have to use that. You cannot normalize it. You cannot divide by negative 2, right? But you're stuck with that vector from P to Q. Okay? You have to use that vector, because otherwise you're changing, well, right? You're changing the vector, and it might not end up at the same point Q. Okay. So, and here's vector v. We know we're going to take the cross product. So the cross product then between these two vectors will be 12 plus 2, so that'll be 14, negative 4 plus 6. Yep, 6 minus 4 is 2. And then negative 2 minus 8 is negative 10. Okay, so we just need the magnitude of that vector, the norm. So square root of 14 squared plus 2 squared plus 10 squared. So that's going to be the square root of, 300, exactly 300, right? And so that's the numerator, square root of 300. The denominator is the square root of v. We already know that that's the square root of 14. So your distance d then is just going to be, well, 300 divided by 14 is 150 over 7. So the square root of 150 over 7, which is approximately, take the square root, 4.6291. Okay, so you have the exact, you have the approximate, good enough. You can even round it, right? 4.63 is probably good enough. Okay, so number 14. Find the standard equation of the sphere with center 2, negative 1, negative 5, tangent to the plane x plus 3y minus z equals 37. Right. So you've done problems in the homework where it's tangent to, say, the xy plane or the yz plane. But here you have some generic plane in space. Right? And we want to find the equation of the sphere. Right, let's say this is the center right here, And we want it to be tangent to the plane. So it just touches the plane, right? Say at this point right here. Okay. So yeah, again, this is a sphere. This is all three-dimensional. Very hard to tell. Yeah, so it doesn't look like an easy problem, right? So yeah, so what do we know? We know the center, of course, right? So we know the x0, y0, and z0. So let's just fill those in, right? This is x minus 2 squared plus y minus negative 1, so y plus 1 squared, plus z plus 5 squared equals, well, what's the radius, right? So that's the question, right? So how do you get r to get r squared in the equation, right? Well, from the picture, we can see, right, this is the radius. I shouldn't use that color. Let me use this, right? So you can see in the picture, it's the distance from the center to the nearest point on the sphere. On the plane, right? So this point right here, right, is a point that's on the sphere, but it's also on the plane. Right, because the plane is tangent to the sphere. Again, it's not clear from the picture. So let me reorient this, right? Suppose this is the sphere, right? And let's suppose the plane is exactly horizontal at the top here, right? Right, so that's our plane, right? Then this point right here is that point that I was just referring to. This purple point corresponds to this point right here. So if we knew the distance from the center to that point, we would have the radius, right? We would have the radius. So yeah, one way to do it is to find that point, right? But that's kind of a hard problem. That's not an easy problem to find essentially the point of intersection with the plane and the sphere, right? Even if we knew the radius, that would still not be an easy question, right? However, we don't really need to know where that point is. We just need the distance between a point, the center, and the plane, right? In other words, the radius is just that distance, d. Right? So how do you find the distance between a point? Again, the point was 2, negative 1, 5. Negative 5, sorry. So same thing here, right? This point here, 2, negative 1, 5. So that's my q, right? And now we just need the distance between a point and the plane. The equation of the plane is, so x plus 3y minus z minus 37 equals 0. Right? So if you're going to use this version, the absolute value of ax0 plus by0 plus cz0 plus d over the square root of a squared plus b squared plus c squared, then yeah, make sure your d is negative 37 and not positive 37. All right, so a is 1, right? B is 3, c is negative 1. And x0, y0, z0 are just these coordinates here. All right, so what do we get? We get 1 times 2 plus b is 3 times y0 is negative 1 plus c is negative 1 times z0 is 5 plus d is negative 37 in absolute value all over the square root of 1 squared plus 3 squared plus 1 squared. So square root of 11, right? And then the numerator, I get the absolute value of negative 43 divided by the square root of 11. So 43 over the square root of 11. Oops, square root of 11, yep. And I knew I was going to mess something up, right? It's a negative 5 for z0. Oops, I had it right up here. I had it wrong down there. All right, so it's not negative 43. Yep, it's negative 33. Oh boy. All right, so that should be a 3. So negative 33 under the square root. So it's a positive 33 divided by the square root of 11. And if you rationalize the denominator, you get 3 square root of 11. Right? Or if you like, the square root of 99. So, yep, that's the radius, right? That's the distance between the plane and that point. So, right, so for the equation, oops, I didn't mean to do that. So for the equation, we know that r is the square root of 99, which means r squared is just 99. So I'm trying to erase that. Okay. 99. So that's the equation of the sphere, right? That's tangent to the given plane with that given center. All right. Yeah, okay, so a little bit of a tricky problem. If you don't draw it, you know, if you draw it correctly, it kind of makes sense, but so yeah. So that's probably the easiest way to do it. There might be other ways, but you know, just find the distance between the plane and the center, and that has to be the radius. Right, so a couple of questions converting to, you know, spherical coordinates and cylindrical coordinates. All right, so 16, we'll do that one first. We're converting the equation in rectangular coordinates, z equals xy, to spherical coordinates. So, I mean, you should, right, I mean, you have the formula sheets, so you have the conversions. Here they are. Sorry, I think I got this wrong. Sine, yeah, so x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. So just plug them in, right? So z is rho cosine phi, x is going to be rho sine phi cosine theta, and then y is going to be rho sine phi sine theta. Right. So on the left, we can leave that alone. On the right, we get rho squared, and then we get sine squared phi cosine theta sine theta. And notice that, right, you know, rho, we can divide by rho because it's not 0, or at least it's not 0 for the entire surface. And I'll write this sine theta cosine theta, right? So if we solve for rho, then we divide by sine squared phi sine theta cosine theta. So rho is going to be, let's see, cosine of phi all over sine squared phi sine theta cosine theta. And I guess that's it. Of course, you can also write this as, well, let's see. So cosine over sine is cotangent times cosecant. So cosecant phi, cotangent phi, and then we just have cosecant and secant of theta. So I guess that's another way to write it. And then 17, similar. So z equals x to the fourth minus y to the fourth, whatever that is. And here we want to convert to cylindrical coordinates, right? So 17, z is x to the fourth minus y to the fourth. And this is in rectangular, we want cylindrical. Right. And then solve for z. So z is still z. We can leave z alone. But x is going to be r times cosine theta. And y is going to be r times sine theta. So you can factor out the r to the fourth, and you just get cosine to the fourth minus sine to the fourth. Which, if you're clever, you can simplify that to cosine squared minus sine squared. And if you're wondering, wait a minute, you can't just change the 4 to a 2, right? Well, remember, this factors as cosine squared minus sine squared times cosine squared plus sine squared, which of course is 1, right? So yeah, amazingly enough, you can just change the 4 to a 2 here. And cosine squared minus sine squared, you can simplify that as cosine of 2 theta. You don't have to, but it probably makes sense, right? So it's already solved for z. I don't know why it says solve for z. You just get r to the 4th times cosine of 2 theta. It's probably the easiest way to write it, most succinct way to write it. Okay, so that's all it is for 16 and 17, just converting to different coordinates. 18 and 19, again, I was almost going to skip these because they're fairly standard. Write the equation of the cone in cylindrical coordinates, right? So if you solve for z squared, you get z squared is 4x squared plus 4y squared. And then just take the square root. Or maybe factor out the 4 first, it doesn't matter. And then take the square root. You get z is going to be plus or minus 2 times the square root of x squared plus y squared. But the square root of x squared plus y squared is also r. So really, it's just z is equal to plus or minus 2 times r. All right, so that's it. Yeah, the minus, I think, is needed here. Because if this is the xy plane, right, this is z equals 0. You get 2 pieces here. You get, 2r, so that should be something like this, right? So that's z equals positive 2r. And then the bottom half here is z equals negative 2r. So you need both the plus and the minus. Yeah, remember r is considered positive, so I think we need the minus. Yeah. All right, 19. Find the angle between the cone, which is z equals 4r, not 2r, so different cone, and the z-axis. Well, right. So here we have this cone and the z-axis. So this is the angle which you could call gamma, but here we just use phi. So we're looking for phi, right? And remember, so phi is in spherical coordinates. So remember, in spherical coordinates, z is rho cosine phi, and r is rho sine phi. So you can divide by rho, and then divide by sine of phi. So you get cosine over sine is cotangent of phi equals 4. Or just flip it over. You can do tangent of phi is equal to 1 over 4. And then just take the arctangent, the arctangent of 1/4. So in degrees, I get 14.04 degrees. Yeah, so a fairly narrow cone. In fact, I drew it a bit exaggerated. But I think that's it. Yeah, that's the central angle. I guess I was going to do radians, but that's not necessary, right? So 18 and 19. And I just realized 18 is wrong, I guess, in the answer key. 18 says z equals 4r. Oh, so there's one mistake. Yep, as I said, some of these are wrong. 18 is wrong in the answer key, so this is correct. So change the 4 to a plus or minus 2. Sorry about that, but I'm glad I did that one then. All right, moving on. Right, so not a lot of proofs on the test, but that said, this one I think is fairly routine if you remember, right? So we're trying to prove the following formula here. Let me write it. The magnitude of u cross v squared plus the absolute value of u dot v squared, right? Remember, u dot v is a scalar, so there's no magnitude around that. That's equal to the magnitude of u squared times the magnitude of v squared. Right? And right, there's a really easy way to do it. If you remember, there's a formula for u cross v, or at least the magnitude of that. Right? It's just the magnitude of u times the magnitude of v times the sine of the angle between vectors u and v. And then u dot v is just the magnitude of u times the magnitude of v times the cosine of the angle. So what happens when you square everything? You just get the magnitude of u times the squared times the magnitude of v. I should do this in yellow now, right? So the magnitude of u cross v squared is the magnitude of u squared times the magnitude of v squared times the sine squared of theta plus, and then an absolute value, right? So these are all going to be positive. The magnitude of u squared times the magnitude of v squared times the cosine of the angle. I guess that should be an absolute value, but you're squaring it, so it's positive, right? Yeah, so when you factor out the magnitude of u squared times the magnitude of v squared, you just get the usual sine squared plus cosine squared, which is equal to 1. So you get what's on the right side, the magnitude of u squared times the magnitude of v squared. So it's really just those two lines. So right, so I think that's a fairly reasonable one. At least now that you've seen it, you should be able to do that on the test at this point. 21, very briefly, where is it continuous where each component is continuous? E to the t is always continuous, right? Log of t plus 3 is only continuous where t plus 3 is positive, right? In other words, where t is greater than negative 3. And t to the 2/3, I think that's continuous everywhere, right? So, yep, I think for part A, it's going to be continuous from negative 3 to infinity. Right. For part B, where is it smooth? Well, that's for the derivative, right? So the derivative of r is e to the t 1 over t plus 1, sorry, 1 over t plus 3, and then 2/3 times t to the negative 1/3. Okay, so I don't think that's ever going to be 0. Right. So we don't have to worry about where it's 0, but we do have to worry about, well, remember, t to the negative 1/3 is 1 over the cube root of t. So you have to exclude 0 as well here. Right? So here you're going from negative 3 to 0, and then from 0 to infinity. Okay, so it's continuous at 0, but not differentiable there. All right, 22. Find a parameterization. Right, so this was 21. 22, find a parameterization of the vector valued function for the segments of the curve y equals the cube root of x between the 2 points, right, -1, -1, and a2. So, right, there's a couple of ways of doing this. One, I'll call R1, the most direct way, right? Let's just say t is x, and then y is going to be the cube root of t, right? So you can do t and then the cube root of t. So if t is x, x is going from -1 to 8, so t is going from -1 to 8. So that's one possible answer. I would prefer to do it the other way. In other words, to say y is equal to t, right? And then x, which is y cubed, would be t cubed. So in that case, we have t cubed comma t, and now, since y is t, y goes from -1 to 2. So now t goes from -1 to 2. So I like that one better because it doesn't have a cube root in it. So not a big deal there, right? And then finally, 23, find a parameterization of the vector valued function for the graph of the ellipse. Okay, well, right, so it's an ellipse is almost like a circle, so you're going to have sines and cosines, presumably. Right, so another way to write the equation of the ellipse is if you have x over 4 squared plus y over 3 squared, that's going to equal 1, right? And hopefully you remember, right, cosine squared plus sine squared is 1. So that tells me that, right, my x over 4 should be cosine, which means x is just 4 times cosine of theta. Oh, let's change theta to t now, right? And then y over 3 is going to be sine of theta. So y is going to be 3 times sine of theta. But let's just use t instead of theta. Right, so those are the parametric equations of the ellipse. Let's write it as a vector valued function, of course. So you get 4 cosine of t times I plus 3 times the sine of t times j. And since if we want the entire ellipse, remember t goes from 0 to 2 pi, since that's the angle. Right, at least it is in this case. T does not have to be the angle, but yeah. So in this case, right, t is theta. Theta is t. So I just interchange the theta and t here. Right, so that's probably the most direct way to get that. Oh, I'm going to start over. Right, and a lot of these going forward now are just straightforward computations. So you're given u and v as vector valued functions, right? And again, v could be velocity, it could be just the position function in terms of v instead of r. So I think part A, very reasonable. So I'll do part B, which is probably the harder of the two, because you're doing a cross product now. So again, I like using the determinant. I'm going to make a little bit more space here, right? So u is 2t, v is t cubed, and z is 1 minus t. And for v, we get t squared, negative 1, and then 1 plus t. So, yep, not pleasant to work out, but for the I component, what do we get? T cubed plus t to the 4th. And then, so plus 1 minus t. All right, good enough. And then plus j, now we have to go backwards here, right? So this is going to be t squared minus t cubed. Sorry, minus t cubed. And then minus 2t squared plus 2t. Minus 2t, rather, right? And then k, you get 2t minus t to the 5th. That was an easy one. But we can simplify this a little bit, right? So how about if I just write it in component form? T to the 4 plus t to the 3 minus t plus 1. And then the second component will be, so negative t cubed minus t squared minus 2t. And then negative t to the 5th plus 2t. So I hope that's right. So that's what it is just in terms of t, right? Okay, so here you're given, again, two vector valued functions, r and u. Part A, basically find the speed of r, right? If r is the position function, take the magnitude of the derivative. So I don't think that's an issue. So how about part B? Take the derivative of the magnitude of r. Okay, so what's the magnitude of r? Well, it's the square root of 3t squared, so 9t squared, plus t squared minus 4t plus 4 plus t to the 4th. So can we simplify this at all? We get t to the 4th plus 10t squared minus 4t plus 4. Sorry, that's ugly looking 4 there. That's better. All right, so now just take its derivative. It's a Calc 1 problem. So if you imagine this is to the power 1/2, you just get 1/2 times t to the fourth minus 10t squared minus 10t squared plus 10t squared, sorry, that's a plus, minus 4 times t plus 4 to the power negative 1/2, and then by the chain rule, the derivative, 4t cubed plus 20t minus 4. Good enough, right? I mean, obviously we can simplify this further, but whatever you get, it's obviously not the same thing as the magnitude of the derivative. So no, you cannot change the order, right? You cannot take the derivative of the magnitude and expect to get the same thing as the magnitude of the derivative of r. Right. Part C, I think you can handle that. In fact, you can do this two ways. You can take the dot product first and then take the derivative, or you can use the product rule for the derivative. Either way works. So let's just do D. We're doing the definite integral from 1 to 3 of r of t. Now, I don't know why you would ever want to do this, right? You're adding up all their positions, right? So at least, you can do the derivative here would at least make a little more sense because you're adding up the velocities and you get sort of the displacement between the first and last position. But I don't even know what this represents, right? But it doesn't matter. When you take the integral from 1 to 3 of this vector 3t, t minus 2, t squared, you just get 3 over 2 t squared in component form, right? But if I just do an I here, right? And then plus 1/2 t squared minus 2t times j, and then plus 1/3 t cubed times k, and now we evaluate between 1 and 3. So I mean, all right, let's do it. So 9/27 over 2 minus, no, I can't do this in my head, right? So t squared, 27 over 2 minus 3 over 2 times I plus 9 over 2 minus 6. So 9 over 2 minus 12 over 2 is negative 3 over 2. All right? And then when you plug in 1, you get 1/2 minus 2, which is, so that's going to be minus negative 3 over 2. Sorry, this is not working out. So negative 3 over 2 plus 3 over 2. I think you just get 0 there, right? And then, yes, 9 minus 1/3. So 27,654. 24 over 2 is 12. So 12i plus 0j, and then plus 26 over 3k. Now, I'm only like half certain that this is right, because I did it awfully fast and I did a lot of the arithmetic in my head. But let's just say that that's it. Yeah, it is the answer in the back, so I trust, I guess I trust it. All right. Okay, 26. So let's see, we have a vector valued function, and this will be a curve in a plane. So r of t is just t to the fourth, t to the negative 1, for t positive. And so for the curve traced out, we want to calculate the unit tangent vector. Okay, so you should know what that is, right? It's just r prime divided by the magnitude of r prime. So r prime is the vector 4t cubed, negative t to the negative 2. And so its magnitude is going to be the square root of 16t to the 6 plus 1 over t to the 4th. And the point is we can simplify this considerably. If we get a common denominator here, this is going to be 16t to the 10th plus 1 all over t to the 4th. And so it's really the square root of 16t to the 10th plus 1 all over t squared. Right? So, yep. So when you divide or multiply by the reciprocal, what do we get here? We're going to get 4t to the 5th over the square root of, I do 1 plus 16t squared, 16t to the 10th. And then the other component will be, let's see, it'll be a negative t to the negative 2 times t to the 2 is just negative 1 over the square root of 1 plus 16t to the 10th. Okay, so part B, find the normal vector n, principal unit normal vector n. And of course, you're not going to do it this way. At least I hope you don't do it this way, because you'll be wasting a lot of time and it's not very pleasant, right? Remember, this is a plane curve. So all we have to do are switch the two components, right? Make y x and x y. Okay, it's not quite that simple, because remember, one of them has to be the opposite. One of them gets a negative sign. So which one is it here? Well, so for that, we need the curve. And let's try to graph it here. X is t to the 4th, y is t to the negative 1. So let's see, if t is the 4th root of x, right, so x to the 1/4, then y is going to be x to the negative 1/4. So what does that look like? Something like this, right? At least for t positive. Oh yeah, t is positive, right? So, so a typical tangent vector will have a positive x and a negative y. Right? That means you're going this way, which means your n will be pointing this way. So both x and y are positive. So which one should get the opposite sign? The first one. We want to make it a positive one, right? So that's it. In fact, I'm just going to erase the positive because it is a 1. And there you go, right? So that's the easiest way to get n. If you're using the definition, you're probably only not even halfway there yet. So, all right, curvature, k, in terms of x. So we want the curvature as a function of x. So you see, now that we did part B here, we know what y is in terms of x, right? Y is just x to the negative 1/4. So to get the curvature, I would use this formula here, the second derivative of y in absolute value, divided by 1 plus the first derivative of y squared to the 3/2. A little sloppy, but I think you get the point, right? So the first derivative is negative 1/4 x to the negative 5/4. And then the second derivative is going to be positive 5/16 x to the negative 9/4. Okay, so 5/16 x to the negative 9/4 divided by 1 plus, so when you square this, you get 1/16 x to the negative 10/4, so that's 5/2, right? 10/4 is 5/2, yeah. Negative 5/2 to the 3/2. Kind of a mess. I'm wondering if we can maybe simplify this a little bit. So this is x to the 9/4, and then we have 1 plus 16, no, 1/16 to the 1/16 times x to the 5/2, and then that's to the power 3/2. So let's see, what can we do? Can we multiply top and bottom by x to the 9/4? Let me make sure that's right. Yeah, I think that's it. So for the numerator then, you're just going to get 5 over 16. Oh, multiply by 16 too. Why not, right? 16. Yep. So now the numerator is just 5. Right? And the denominator, so if we have to bring this inside to the square root and cube it, this might not be as easy as I thought. That means we write this to the power 2/3 then, right? So 9 over 4 times 2/3 is just going to be 3 over 2, so that helps. And then 16 to the 2/3. Well, let's see, the cube root of 16. Oh. I don't know why I'm doing this. I mean, this is, this is fine, but I just don't know if it's necessary here to bring this inside. We might have done better just to leave it on the outside and then simplify this. So yeah, let's take that root here. So leave the 16 x to the 9 over 4 on the outside. And then for the inside, we have 16 x to the 5 halves plus 1 over 16 x to the 5 halves to the 3 halves. And yeah. So now what happens on the outside? So this I think is fine on the inside. And then on the outside, so we divide by 16 to the 3 halves. Oh, we had to do that anyways. And then x to the 15 over 4. Really? 15 over 4? Yeah, I think so. All right. So that goes on top. We get 5x to the 15 over 4, whatever that is, divided by, so I think the 16 to the 3 halves divided by 16, you just get square root of 16, which is 4. Right? And then over 1 plus, oh, there's still a 3 halves here, though, right? So 1 plus 16x to the 5 over 4 to the 3 halves. So, and again, I'm only half certain this is right. Yeah, everything except the 15 over 4. So where did I get that from? I did 5 over 2 times 3 over 2. Should it have been divided by 3? No. 3 over 2. It looks like 15 over 4 to me, so... Well, I would go with this. I don't know where I got the 3 over 2 from. Yep, I mean... So that could be a mistake in the answer key again. It looks to me like 15 over 4, not 3 over 2. But might have done something else wrong. Oh, okay. So I forgot the x to the 9 over 4. There we go. So 15 over 4 minus 9 over 4 is 6 over 4. There's the 3 over 2. So it is 3 over 2. All right. So not a mistake. Well, not in the answer key. I made the mistake here. Okay. So this 15 over 4 should be 3 over 2. Yeah. Yeah. Because I forgot the x to the 9 over 4 here. Okay. So all right. So that's right. X to the 3 over 2. Oh, we didn't divide yet. So this is the 15 over 4. That was correct. But then when you subtract the exponents, you do get 3 over 2. Phew. Okay, that's k in terms of x. And then there was one more. Oh, find the maximum curvature. So that's a Calc 1 problem. I think I'll let you do that. Right? How do you maximize a function? Take the derivative, right? Set it equal to 0. Right? You're finding the critical numbers in terms of x. So yeah, so now that we found k as a function of x, now you just have to take its derivative. Quotient rule, chain rule, all that business. Yeah, and not an easy Calc 1 problem, but it is a Calc 1 problem. So I think you can handle that, right? Solve this equation for x, and then plug that into k to actually get the maximum curvature, right? So you solve for x, right? So say you get x0 or something, then you plug that into k, and then that is the maximum curvature. Okay, so not a hard problem, but kind of a tedious one. Okay. Okay, so 27, 28. I think 28 is going to be considerably harder because 27 is a plane curve. 28 is a curve in space. So, yep. So you know the drill there. We've done it once already. Yeah, honestly, I'm not looking forward to this, but let's see. Maybe it's not as bad as I think, right? So remember, t is just r prime over the magnitude of r prime. So r prime is just, well, I plus 2j plus 2t times k. And then taking the norm of that vector, you get the square root of 1 squared plus 2 squared plus 4t squared. Right, so you get the square root of 5 plus 4t squared. So t as a vector is just going to be, so I plus 2j plus 2tk all over this square root. Okay, right, so you can leave it like that. That's right. So how do we find the principal unit normal vector? Well, yep, t prime over the magnitude of t prime. Or, I found this formula in the book. It's in 12.4. Right? Remember, I did say that this is not the only way to calculate the unit normal vector. Certainly if it's a space curve, we did one like that earlier, where you can just do that trick of switching the component. But this is a vector in space, right? So there's no switching there. So I found this formula, and obviously this might be a little bit easier. I mean, it looks horrible. It looks like a nuisance, but we already know what v is, right? V is r prime. So it's just this vector here. And a is the acceleration. That's the derivative of v, which is 0, 0, 2. Right? So taking the dot product of these, I don't think is going to be all that bad. So I'm going to do it this way, and I'm hoping that it's a lot easier than just using the straightforward definition. Right. And so, yeah, you're welcome to use it. Now, the problem is I didn't put this on the formula sheet. Right. So, look, very likely I'm not going to ask this on a test. If I do, I'm just making it needlessly tedious. So this would be a good project, I guess, but not good for a quick, for a quick 2-hour test. All right, so let's just take each of these separately. What's v dot v? Well, that's just the magnitude of v squared. We already did the magnitude of v, so when you square it, you get 5 plus 4t squared, right? And then that'll be times the vector a. So what's v dot a? So that's just going to be, well, 0 plus 0 plus 4t. So it's just 4t, right? Okay, so I think putting this all together, the unit vector n, that looks like a w, so n is just going to be 5 plus 4t squared. Oops, sorry, 4t squared times the vector a. We'll write that down in components next time, right? Minus 4t times the vector v, all divided by its magnitude. I'll just put a little arrow because we'll do the magnitude after we calculate this, right? All right, so yeah, so 5 plus 4t squared times the vector with components 0, 0, 2, minus 4t times the vector with components 1, 2, 2t. Right, and divided by the magnitude. Okay. So, right, so the numerator, you're going to have components 0, 0, and then it looks like 10 plus 8t squared plus, or minus, right? Minus, yep. The vector with components 4t, 8t, and then 8t squared. And again, don't forget to divide by the magnitude. So what is this vector? We just get negative 4t, negative 8 times t, and then 10 plus 8t squared minus 8t squared is just 10. Right. So divide by its magnitude. So its magnitude will be, right, square root of 16t squared plus 64t squared plus 100. And 16 plus 64 is 80. T squared plus 100. And we can factor out 4. Can we do 16? No, so we can do a 4. So 2 square root of, let's see, divide by 4 is 20. So 20t squared plus 25. Yeah. So 2 square root of 20t squared plus 25. And yeah, you can divide each of these by 2, right? So let me go back and write it in ijk form. So this will be negative 2t times I minus 4t times j plus 5 times k, all divided by this square root of 20t squared plus 25. So, and again, I did that awfully fast. I'm not sure it's correct. So was that easier than using this? I don't know. I think so. I think it was more fun. I kind of like this better than, figuring out the derivative using the quotient rule and all that. So yeah, I like this better. Of course, you have to know the formula then, but it's in the book, so look it up. Right. It's in the exercises in 12.4, if that helps. All right. And then the tangential and normal accelerations. I think that's pretty routine here, right? Oh, but let's do it. Right, so the tangential acceleration is just a dot t. So I had to go back up here for t, and then the dot product of a. Remember, a is just 0, 0, 2. So yeah, so this is just going to be 4 times t divided by the square root of 5 plus 4t squared. Right. Remember, it's a scalar, right? And then for part D, the normal acceleration, well, you could, at this point, you can just as easily take a dot n because here's n, right? So yep, so a only has a k component, a z component, so it's just 2 times 5, which is 10, divided by the square root of, wait a minute, yeah, 20t squared plus 25. Which yeah, I guess we can factor out a 5 here, right? Square root of 5. And then this would just be the square root of 4t squared plus 5. 5 plus 4t squared. Okay. Just to make it look pretty similar here. So this is 2 square root of 5 all over the square root of 5 plus 4t squared. Okay, so that is the normal acceleration, or centripetal acceleration, if you remember. Okay, and finally, I think it's the curvature. Yep, so now we want the curvature, K. And there's a whole bunch of formulas on your formula sheets. You know which one I like best is actually not a formula for K, but the normal acceleration, remember, is K times the derivative of s squared, right? Now the derivative of s is just the magnitude of v squared. And if you remember, the magnitude of v was square root of 5 plus 4t squared. So this is just going to be k times 5 plus 4t squared. Right? And we know what the normal acceleration is. We just did that in part D. So that's going to be 2 square root of 5 divided by the square root of 5 plus 4t squared. So when you divide, k is just going to be 2 square root of 5 divided by 5 plus 4t squared to the 1 plus a half is 3 over 2. Okay. So, yeah, kind of a shortcut there. Again, all the other formulas work. Again, you can't use the one for curves in a plane. This is not a curve in a plane. This is a space curve. So I think the other reasonable one would be the magnitude of r prime cross r double prime, and then divided by the magnitude of r prime cubed. So you would have had to take v cross a, which is not hard, right? And then divide by the magnitude of v cubed. So that would have worked probably just as well. All right, so a bit of a hard one, especially part B. B is a big nuisance here, and it's not something I would ask on a test. Unless I gave you if I gave you this formula and gave you R, you know, especially with a very simple V and A, this is not a very difficult question. I guess that would be reasonable, I think. That would be a reasonable test question, but not if you're going to do it by the original definition, which would take forever. So a lot longer than this, I would imagine. All right. All right, and finally the last two. So number 31, a baseball is hit from a height of 3.5 feet above the ground with an initial speed of 120 feet per second at an angle with 30 degrees to the horizontal. So yeah, just draw the picture here. So here's the horizontal, that's x, this is y. 3.5 feet above the ground, let's say right here, and 30 degrees, right? It's going to do this. Right, so the initial speed, oops, a little too steep there. And that's still not right, but, you know, 120 feet per second. Close enough. Find the maximum height of the baseball. So that's a reasonable question, right? This is the maximum height. And then there's a second part. Determine whether it clears a fence 375 feet away from home plate. So, all right, so let's say this is 375 feet. And the fence is 8 feet high. Well, yeah, I mean, I'm drawing it so that the answer is yes, it does clear it. But if 8 feet high is this, then no, then it will bounce off the fence. So that's the question, right? Does it clear the fence? This is 8 feet high, right? Yeah. So 2 questions, right? First, the maximum height. I think that's probably the easy part, because what happens at the maximum height? Right, the ball is traveling horizontally. In other words, the vertical component of the velocity is 0. Okay, so let's get the equations, right? We know that the acceleration is just negative g times j. G here is negative 32 feet per second squared, because we're in feet, not meters. So the velocity then will just be, well, the initial velocity plus the acceleration times time. And so should we split these into components already? Sure. So let's do the horizontal component, right? So Vx is just going to be Vx0, right? And this doesn't contribute anything. Yeah. So this Vx0 is just V0 times the cosine of theta. Theta here is 30 degrees. Right. And V0 is 120. So putting that in your calculator, you get 103.92. Oh, cosine of 30 degrees, right, is square root of 3 over 2. So it's 60 times the square root of 3. So that's the exact, approximately 103.92. And this will be in feet per second, of course. Right, so that's a constant horizontal velocity, right? The vertical component, Vy, will be Vy0 minus gt. Right, so Vy0 is, again, V0 times the sine of 30 degrees. 0 sine of 30 degrees minus 32 times t. And sine of 30 degrees is 1/2, so this is just 60 minus 32t. Right, so for your position vector, you're going to get an x, which is just going to be your initial x, which we might as well call 0. So x0 is 0. And then Vx0, so that's going to be the 60 square root of 3 times t. I guess that's it, right? And then for y, well, you're going to get y0, which is 3.5 feet, plus V0t. So, okay, so Vy times t, right? Oh, I know why I'm getting confused. I'm not integrating correctly here. Yeah, so V0y times t. V0y is just the 60. So 60 times t minus 1/2 gt squared. So that's minus the 16t squared. Okay, so I think that's right. Yeah, when you integrate this, you get, 60t minus 16t squared. Good enough. All right, then. Okay, so to answer the first question, what is the maximum height? So to find how long it takes to get there, you set this equal to 0, right? In other words, you set the vertical component of y equal to 0. Right. So 60 minus 32t equals 0. So t is going to be 60 divided by 32, which is 30 divided by 16, which is 15 divided by 8. So 15 over 8 seconds. Okay. So that's how long it takes to reach the maximum height. What is the maximum height? Plug this in for y now, right? So y, maximum y, right, will be 3.5 plus 60 times t, 15 over 8, minus 16 times t, 15 over 8 squared. Yeah, just plug it into a calculator, and I get 59.75 feet. Right. Yeah, 3/4 of a foot is what, 9 inches? So, yeah, you can also say 59 feet, 9 inches. All right, so part B then, oh yeah, determine whether it clears a wall, sorry, a fence 8 feet tall. So here's one way to go about it, right? We can determine the height of the ball when x is 375, right? So when x is 375, so this will be part B here. So yeah, so when x is 375, what is t? So x is 60 square root of 3 times t. So t is just going to be 375 divided by 60 root 3. We might as well just approximate that. I get 3.608. Oh, 3.6084. So that's how long it takes to get to that position, right? And now, how high is it? Is it bigger than 8 feet or less than 8 feet? So when you plug that into y, right, and I'm not going to write it, well, okay, I'll write it down. 3.5 plus 60 times 3.6084 minus 16 times 3.6084 squared. So if this is bigger than 8, the answer is yes, it does clear the fence. And if it's less than 8, then it doesn't. And if it's exactly 8, it kind of just bounces off the top of the fence, I guess, right? Yeah, so it's not exactly 8. It's actually 11.6752 feet. Obviously, you know, whether you round to the nearest hundredth doesn't matter. So this is definitely bigger than 8 feet. So the answer to part B is yes, it clears the fence. Okay. Yeah, so I think that's the easiest way. Find the height of the ball at that position, and if it's bigger than 8 feet, it clears the fence, and if it's less than 8 feet, it doesn't. So since 11 feet is bigger than 8 feet, it definitely goes over the fence, right? So it's a home run. It's a home run. Right, so that's 31. And then everyone's favorites, this number 32. So this is the last one, and this is, obviously this is going to be a challenging one. And a lot of it is, because it's three-dimensional, right? And it's very easy to get lost in what's really going on here. So Emily, standing at the outer edge of a merry-go-round, which is 10 meters from the center. So let's draw it from the top point of view here. The merry-go-round is circular, right? Here's the center. And we know the radius, right, is just 10 meters. Let me fix that, 10 meters. Kind of a big one, but okay. And it completes one revolution every 20 seconds. So one revolution every 20 seconds. What is that? That's the rate of rotation. I don't know. Are we going counterclockwise, clockwise? I don't know. Which way do they go? I'm trying to envision it going. I think it, well, I guess they can go either way, but let's say counterclockwise here, right? So that's just the angular velocity, right? That's my omega. So one thing it might be helpful to do here is to get proper units. A revolution is 2 pi radians, right? So this is really going to be pi over 10 radians per second. Okay. So again, it's a little bit of unit issue there. You can't leave it as revolutions. A revolution is one complete cycle, 2 pi radians, right? Or 360 degrees, but here it makes more sense to use radians. All right, during the ride, Emily drops a ball from a point, P, 2 meters above the ground. Okay, so let's say point P is right here. But, right, this is only from the top. So now we need a view from the side. Okay, So here's the carousel. So this is the platform, right? And Emily is standing right here, right, with the ball right here. And this is 2 meters above the ground. That's a pretty high platform. Yeah, I mean, okay, so this is a weird problem, right? So I hope Emily doesn't fall off because that's like 7 feet. But in any event, okay, so this is 2 meters above the ground, let's say. Right. And so Emily drops the ball at that point, right? Now, remember, the carousel is moving, so at this point it looks like it's going this way. So when Emily drops the ball, it doesn't just fall straight down, right? Maybe from her point of view it does, but from someone on the ground, right, it has a horizontal component of the velocity, right? It has an initial horizontal velocity, right? Maybe not a very big one. It's the speed of the carousel at that point. But yeah, it has a horizontal component. So what happens after you release the ball? It takes a parabolic trajectory. Okay? So remember, point P is the point of release. So the question A is, how far from P is the ball when it hits the ground? So here, let's call this point Q, where it hits the ground. Right, so what's that distance? The distance between P and Q. Okay? So what we need to figure out is essentially the distance. We need the 2 points. We need the coordinates of those points. Okay? So where's our coordinates, right? X, Y, Z. So how about if we make the center of the carousel our origin, 0, 0, right? So P then will be, well, 10 meters north of there. So if this is X and this is Y, X will still be 0 at point P. Y will be 10. And Z will be, well, 2, because that's the height, right? So point P, I want to make that clear here, point P has coordinates 0, 10, 2. Okay. So now we need the coordinates for Q. Where does it land? Right. So from this point of view, for looking from above, right, the ball is being thrown this way, and it lands somewhere over here at point Q. Okay? So the y-coordinate doesn't change. The y-coordinate will still be 10. Right? The z-coordinate, well, it's on the ground, so z is 0. So the only issue is, what is the x-coordinate here of where it lands? Okay, so that's the hard part, right? Because that has to do with this trajectory, right? This projectile motion. Right. So first of all, what is v0 here? What is the initial velocity of the ball? Well, it's only moving horizontally, right? Because Emily's dropping it, not throwing it, right? It's not being thrown downward this way, for example, right? So yeah, when you drop something, it starts with initial velocity 0, at least vertically. So what is the speed of the carousel at that point? Well, that's just omega times the radius. Omega, we said, was pi over 10, and the radius is 10 meters. So the initial velocity is just pi, right? Pi meters per second, so about 3.14 meters per second. Okay? So that's the initial horizontal velocity. So v0x is just pi. Right, so v0y is 0. Right, so x is just going to be v0x times t, so pi times t. Yeah, I think that's it, right? And then y is going to be y0, which is 2, plus v0y, which is 0, minus 1/2 gt squared. So 1/2 gt is 4.9 t squared, right? Okay, I think that's it. So when the ball is on the ground where v is 0, oh, sorry. Now I'm mixing up my y's and z's here. Yep, sorry, y is always 10. This is z here. right? This is also a z here. Right. So this is the height of the ball, z. Okay, good. Okay, so when is z equal to 0? Right, we can solve that. T squared is just 2 over 4.9. And so the square root of that, square root of 1 over, oh gosh, so 2.55, 2.45. Okay, so 4.9 divided by 2. Yep, 2.45. So take the reciprocal and then take the square root. So this is approximately 0.6389. So how about 639? Or how about just 0.64? 0.64 seconds. Right, so that's how long it takes essentially to drop to the ground. A little more than half a second, right? Roughly 2/3 of a second. Okay, so if that's t, now we can find x. X is the horizontal distance it travels. Right, x is just pi times t, which is pi times 0.64. So multiplying by pi, we get about, 2 meters? I get exactly 2.0, not exactly, but about 2.007 meters. Okay, so I'll keep the 0.007. Okay, so 2.007 meters here. Okay, so look, we're almost done. This is our x1, y1, z1. This is our x2, y2, z2. Find the distance between those 2 points. Okay, so that's just the usual distance formula. So the difference in the x's is 2.007 squared plus 10 minus 10 is 0 squared plus, and then 2 minus 0 squared. So this is approximately, hang on. Okay, so it's about the square root of 8.028. Square root of 8.028, which is about 2.833. We'll say 2.83 meters. So I think that's the distance. Yep, that's the distance between point P and Q, from where it starts to where it lands, where it was dropped from to where it lands. All right, and that's only part A. That was hard enough, right? Part B, how far from Emily is the ball when it hits the ground? So we know where the ball is when it hits the ground. That's point Q. Where is Emily? Right. So here's what happened, right? In that amount of time, Emily presumably just stood there and moved a little bit this way. So Emily is right about here from the top view, and let's say Emily is right around here. So, well, that looks a little too close. Maybe right about here, right? So we'll call this position E, and we want the distance to position Q, to point Q. Okay. So yeah, Emily is just on the edge of the carousel here. Boy, I really messed that up here, right? So, yes. So it's somewhere on the circumference of the circle. This might be a good time to just start over and draw that circle again here, right? So this was your point P. This was where Emily dropped the ball. And then Emily moved through some angle. We can call that theta if you want. To this point here. Okay. So, right. So what are the coordinates here? Well, we can just use sine and cosine. Okay. This is a right angle. So first of all, what is that angle? It's omega t. Omega, remember, was just pi over 10. And t was where was t? Oh, 0.64 seconds. 0.64 seconds. So that gives us about 0.201 radians. Yep, we'll stick with radians here. Or maybe not. How about degrees? Divided by pi. Oops. All right. 11.52 degrees. Okay. So that's how long the ball was in the air. So when it lands, Emily has moved through that angle. And so let's see, what I call the y-coordinates is going to be cosine, 10 cosine, that angle. Yep. So the y-coordinate will be, for Emily at this point, so ye will be 10 times the cosine of 11.52 degrees. And now the x for Emily will be 10 times the sine of 11.52 degrees. I know it looks like it should be negative because it's to the left, but in this picture here, it's moving to the right. Right? When you're looking from this point of view here, it looks like it's going to the right, right? Okay, so plug those in. I'm in degree mode, right? Yeah. So this will be about 9.7986. How about 9.799? And then here, sine of 52 degrees, sorry, 11.52 degrees is 1.997. Again, these are in meters. Everything's in meters here. So those are the coordinates of Emily. 1.997, 9.799, and again, 2 meters above the ground. So, and remember, point Q has coordinates 2.00710. Right. So you're doing the same distance formula, right? The distance between E and Q, yeah, is just the square root of all this mess here. 0.007 minus 1.997, so that's really just 0.1 squared, and then 10 minus 9.799, 0.201, yeah, okay, 0.201 squared, and then 2 minus 0 is 2 squared, right? So this is the square root of 4.0405. So it should be just a little bit above 2. Yep, 2.01, almost exactly. So 2.01 meters. Right, it's 2.0101 if you really want to be precise about it. See, I'm getting sloppy here. 2.0101 meters. But I guess we're rounding to 2 decimal places, so that's fine. Of course, it's good to keep 3 decimal places here for just accuracy. So yeah, again, you have to look at it from the top view, from the side view. It's a geometry problem, and it's highly visual. You have to visualize 3 dimensions this way. Either that or build a 3-dimensional model of the merry-go-round and all that stuff, but that's not practical. That could take a while. So there you go. I hope this helps. And yeah, I mean, look, if you're probably wondering, would I put this on an exam? again, it depends on the exam, right? I mean, for a timed 2-hour test in class, this is probably not reasonable. For a take-home test or a project or a problem set, this is reasonable. It might take you a few hours, but for that, it's a fair question, but not for a timed test in class, let's say. In any event, it's a hard problem, right? It's not an easy problem. But I hope this at least helps. Again, my pictures are a little sloppy. Sorry about that, but that should do it. So that concludes my review for the first test. And best of luck.